One of the problems with treating evolution as a principle of life is that, sure, like genomes can be observed as changing. That's very obvious. Parents are very different from their children in a lot of ways, and their genomes, and in a way that even genomes are like devolving. That every generation has more mutations than the last, and that's observable. But large-scale changes of species going from a certain kind to another kind are not observable. They haven't been observed in modern science, and the only thing that we have to claim that would be the fossil record, which can be viewed in very different ways. One thing that changes from parents to children is in the genome is an accumulation of mutations. Actually, a lot of scientists think that the human lifespan actually is getting shorter over the years because of the mutations that are building up. Virtually all of which are non-beneficial or don't have any benefit to them. A lot of these mutations, like they increase the risk for cancer, they increase the risk for other diseases, and really a lot of scientists think that because of modern medicine we're able to live longer. The accumulation of mutations in the genome probably shortens a person's lifespan significantly. If someone, even though this never really happened in the 1700s, in the 1700s people would die early of conditions that are very preventable today. If someone lived out their years and had a good healthy diet, they probably would have lived longer than they would have today doing that same thing. It's just that today modern medicine allows us not to die of appendicitis or the flu or whatever, so that the average lifespan is longer. The newest field in biochemistry, one of the biggest discoveries of recent years has been of epigenetics, which literally means above the genome. There was a big race decode the genome before this, but now there is literally above the genome is what it means. So there are certain characteristics of the DNA that make it interact in different ways. One of these main things is DNA methylation marks. Certain DNA strands will be methylated in one way, in one place or another place, and even indicates from which parent you got it in. So you could receive genetically the same DNA from a mother or father, but depending on which parent you received it from, it may interact in different ways because of the methylation on it, depending on which chromosome it came from. And so one of these things is that scientists are increasingly discovering how complex the genome is this way, how it will fold based on different methylation marks, different interactions in different organizations of the epigenome, and how it interacts and displays its genes. It makes certain genes presentable in different parts of the body, it makes certain genes presentable in another part. One way the epigenome is increasingly challenged modern evolution is that with the discovery of how the genome interacts and sequences in the DNA that we previously thought were useless, and how they actually interact to make the DNA have its genome interact in a different way, or be able to code a different protein or express something else. We've increasingly seen that the amount of junk DNA, like DNA that we didn't know the function of, so we classified it as junk, has decreased dramatically. It seems that every time we analyze a certain percentage of the epigenome, which we've only analyzed a very, very, very small percent of, that every time we analyze it, we discover more and more functions for parts of the genome that were previously thought to be as useless, or just junk DNA, or fill-ins from ancestors that don't mean anything, or just viral inserts or anything like that. One of the things actually is viral inserts we thought were very useless before. They actually play a part in immunity.